spectroscopy, this is actually under one spectroscopy technique. It's a huge topic actually. Okay, it's a huge topic to understand on the infrared spectroscopy. But for this talk, you are going to learn the basic principle behind the infrared spectroscopy. Okay, and then after that, maybe on January, I think, we are going to have another seminar series on the interpretation, and then after that, we are focusing on the results that you get from the infrared spectroscopy. Okay. I think here we have the audience here from bioscience student, and also from the bioscience staff. Okay. Because my talk today is focusing on the bioscience student lah. Okay. When we talk about the instrument ni, it's actually the basic principle behind the instrumentation tu is more on the physics. If you go to the UVIS seminar series under physics department, so they are talking about the physics what they call this, behind the basic principle of the instrumentation in term of the physics. Kalau if you talking about the chemistry also, the interaction between the what they call this, the spectroscopy technique, spectroscopy, the photon, for example, with the molecules, something like that. So for this one, for this talk, we are focusing, I will not go into deep on the basic principle, okay, on the physics side of the infrared spectroscopy. I'm just focusing on the surface so that all of the students can understand the basic principle behind that, behind the infrared spectroscopy. Okay, so with the aim that once you run your sample using this instrument, you know what actually happened between the instrument and also your sample. So that's very important lah. Okay, so that's why the most important is to understand the basic principle. After that, once you understand this basic principle, and then after that you can interpret the result that you obtain from the infrared spectroscopy. Okay. Okay, let's go to the next slide. So this is the content of my talk today, talking about first introduction, second knowing your sample. So this is also really important. Examples of the IR spectra and also IR spectrum, correlation chart. So what is the correlation chart? I will tell you about this. Functional groups or bonding in the samples, interaction between molecules and also infrared lights, and finally the molecular vibration. Okay, so spectroscopy. So infrared spectroscopy is one of the spectroscopic technique. Okay, we go to the definition of the spectroscopy. It is a interaction between radiation and also molecule and or ions. Interaction between radiation and molecules or ions. So the instrument that we use for this technique, we call it a spectrophotometer or spectrometer. We call it spectrophotometer because some of the instrument involve photon, okay, or lights. So in this case, in the infrared spectroscopy, we're using infrared light. Techniques, sometimes we call it a spectroscopic technique, okay. The results that we obtain from this spectroscopy, we call it as a spectrum or spectra. Spectra is the plural for the spectrum. It's not spectrums, okay, it's the spectra. Okay, so we call it as a IR spectra, infrared spectra. Sometimes we call it as FTIR spectra, FTIR spectrum. FT refer to Fourier transform infrared, FTIR. Okay, or sometimes we call it just IR spectrum, IR spectrum. Okay, so these are the examples of the spectroscopic techniques, such as UV visible, infrared or Fourier transform infrared spectroscopy, nuclear magnetic resonance (NMR), or mass spectrometry. So all of these spectroscopic techniques are used to identify the organic compound. Okay, mostly used to identify and then to characterize organic compound. Okay, so what is infrared spectroscopy? It's one of the spectroscopic technique that serve as a tool for structure determination in the organic chemistry. Okay, however, we can also use this infrared spectroscopy for characterization of inorganic compound. Okay, IR spectroscopy observe the vibration of bonds. So when there is an interaction between IR lights and also molecules, there will be a vibration will occur, and there will be some energy that will generate from this vibration, and then after that we got the IR spectrum or FTIR spectrum. And based on this vibration of bonds, it will provide evidence of the functional group. I will show you what are the functional group. Okay, so the term Fourier transform infrared spectroscopy is come from what they call this, the techniques on how they convert the raw data into the actual spectrum. So Fourier transform is the mathematical process lah, to convert the raw data that they obtain from the instrument, and we got this IR spectrum. Okay, these are the spectrometer. Okay, once we the instrument that we have in T02 is at the center here. Okay, this one. Okay, so this one. We have from thermoscientific. Okay, no, this one. Okay, so this one. We have thermoscientific. Okay, just a simple one. This is a desktop infrared spectrophotometer. Okay, so this is the sample holder. We just only have one only. Okay, but the sample holder here can be changed. This one is using attenuated total reflectance (ATR). ATR is one of the sample preparation techniques for the infrared spectroscopy. ATR. For the ATR, it's very simple. We just put our sample, for example, in the powder form or in the liquid form. We put it on top of the sample holder, and then there is actually one laptop here that connect to this spectrophotometer, and then we got the spectrum. So this one we are using the KBR technique. So we just replace the sample holder here, and then we can use different sample preparation. So this one we are using KBR technique. KBR is potassium bromide. We need to come up with the KBR disk together with the sample inside that, and then we need to put it inside this sample holder, and then we will get the IR spectrum from the computer. Okay, but this is the latest technique lah. Not the latest actually. It's much more convenient than using KBR. But there is limitation. There are some limitation if you want to study more about the sample. So actually you need to have a KBR technique. So this one we using what they call this, the ATR technique. So remember, it's not the ATR spectroscopy. Sometimes they call it as ATR, FTIR, ATR, FTIR spectroscopy. Okay, because ATR is using this sample preparation. It's not ATR spectroscopy. Okay, you need to combine it together, ATR, FTIR spectroscopy. But sometimes we just only call the spectrum as FTIR spectrum only. No need ATR. Okay. And this spectrometer can be used to analyze the different sample state. Okay, we can use in the powder state, in the solid. Okay, solid, liquid, and also gas. But for the gas is a little bit different because we need to capture the gas inside here. So there is a some special accessories if we want to use gas. Okay, and then there is this one is just simple one. There is a big one, so the big one is much more what do you call this? The resolution is very high as compared to the lower spec here, and there is a different branding. Okay, this is the newer the newest. Okay, we put it the FTIR technique, and then it shows the IR spectrum here. But this is what we call it as benchtop lah. There is a comparison between benchtop and also the big one. Okay, for the benchtop is limited to just to get the data. Okay, to get the IR spectrum. But for the big one, we can use it for various application. Okay, so this is the overview of the spectrometer. Okay, if it's not working at T02 at our building, actually there are FTIR spectrometer you can see at the UPMU T03, or there is also a spectrometer under Department of Chemistry or at T05, but they have different brand, but the concept is almost the same. Okay. Sometimes the infrared spectrophotometer is combined together with thermogravimetric analysis. So actually we have this instrument in UPMU T03. Okay, so once we give a heat or we give a different temperature of the sample, so some of the elements or compounds in the sample will evaporate, and this evaporation compound will go to the infrared infrared spectroscopy, and we will know what are the compounds that release or decompose from the sample. Okay, but this one is a little bit complicated as compared to the previous one. Okay. Okay, so knowing your sample, so it's very important. Before you want to analyze your samples using infrared spectroscopy, you need to understand what kind of sample that you have. Okay, this is just very basic. Okay, if you learn organic chemistry during the degree, actually I teach a subject organic chemistry, so I mentioned about the difference between organic and also inorganic compound, and then I teach about me and also Dr. Razauddin. We teach a subject bioorganic chemistry. So under this subject organic chemistry, we need to learn the functional groups, the bonding, the what they call this functional groups lah. This is very important lah, functional group, and some of the biomolecules before we proceed for the analysis using infrared spectroscopy. So that's why the first thing you need to know is to know the what kind of sample that you have, whether it is organic compound or inorganic compound. And some of them, they have hybrid, organic, inorganic compound. Okay. So what is the organic compound? Organic compound, if you can see the difference here, is contain carbon, contain other elements and found in organism. So it has a CH, CC here, contains carbon and hydrogen, and some of them they have OH, NH. So this is organic compound. For the inorganic compound, okay, so it do not usually contain carbon. It's come from the periodic table. Okay, for example, like sodium chloride. So this is inorganic compound, and it's involve ionic or covalent. There is no CH group. Okay, carbon nanotube. Carbon nanotube is just contain C bonding with C. So that one actually fall under inorganic compound because it does not have a CH. Graphene also fall under inorganic compounds. Graphene also is contain CC. Okay, C and C, there is no H. Unless we do some surface modification. For example, like we functionalize the surface of the graphene. We functionalize the surface of carbon nanotube. So in that sample, we have two parts. One is the organic compound, another one is inorganic compound. So we call it as hybrid organic and inorganic compound. Okay, why is important to know your sample? Okay, because it's related to the interpretation of IR spectrum. The result that you will get after you analyze the sample using IR, using this instrument. Okay, because if you come up with if you do not understand what is your sample, it's hard for you to interpret the IR spectrum. Okay, so organic versus inorganic compounds here. Organic compounds contain carbon usually bonded to hydrogen, for example, DNA, sugar, methane, or ethanol. Ethanol. Methane is in the form of gas. Ethanol is in the form of liquid. Okay, inorganic compounds usually don't contain carbon, for example, table salt, hydrochloric acid, quartz. Quartz is a silica, carbon dioxide. Inorganic carbon compounds include carbon dioxide and some carbonates, cyanide and carbide. So those are different between organic and also inorganic compounds. Okay, so these are the organic compounds. You can see the organic compound contain CC and also CH. For example, like ethanol or bioethanol. Bioethanol is ethanol, but the source is different. So it's contain CH and also OH and also CC. Okay. Cellulose structure. For example, you extract cellulose from bacteria. Okay, bacterial cellulose. Or you extract cellulose from plant. So in the cellulose there are CO. So this is the structure of cellulose. Here is represent carbon. There is a carbon here. There is a CC, CO, OC or CO, OH. So it's contain a lot of OH bonding here. Okay. Benzoic acid. Benzoic acid, you can see there is a C double bond C as a bonding. C double bond O, OH. Salicylic acid is contain OH. OH, C double bond O, C double bond C. Okay. Quercetin, one of the bioactive compound from the plant. So it's contain aromatic compound, and under this aromatic compound there is a C double bond C, CO, and so on. Okay, so these are the example of organic compound. Why is really important? Because the infrared lights will interact with the bonding inside the sample, and then after that it will give energy, and based on the Fourier transform, based on the mathematical model using Fourier transform, it will convert to the IR spectrum. Okay, so there is a relation with that. So that's what theoretically, a pure, highly pure carbon nanotube will not give any peaks in the IR spectrum. It just only give one line only. But if there is some impurities or some what do you call this, water compound in the carbon nanotube, it will give some peaks there. Okay. So what do you need to know? Sekejap. Okay, what do you need to know? You need to understand before you can interpret the IR spectrum. These are the things lah. First is infrared theory. Second, type of material, especially the structure of compound. But it's okay if you do not know the structure of compound. It's okay as long as you know that whether it is organic compound or inorganic compound. For the organic compound, you need to understand some basic organic chemistry. Okay, because it's related to the naming of these organic compounds using IUPAC system, and some of the functional groups, important functional group like OH, NH, CH, and C double bond O, and this and also the bonding. the bonding. OH is the bonding. There is a bonding between O and H. There is a bonding. Okay, there is a bonding between C and H. There is a bonding between C and O. So those are bonding and also correlation chart. This is the typical process of structural identification of an unknown sample. Okay, first you get the unknown sample. If you want to know the structure of this unknown sample, you will get the IR spectrum. And then from that IR spectrum, you interpret using correlation chart. And then from that correlation chart, from that interpretation, you will know that inside this sample, there are certain important functional group, such as CH, OH, or NH. And then the result from here need to combine with other instruments. For example, like using NMR, mass spectrometry, UVIS, and finally you can come up with the structure and some other important elements. For example, like you can get melting point or boiling point and so on. Okay. So from here, actually, what we can say, if you use IR spectrum alone, you cannot come up with the structure, with the specific structure. You need to have a combination with other instrument. Unless you have a very highly pure sample, and you know some of the important information. For example, like you know the what do you call this? You get the result from mass spectrometry, something like that. Okay, and then after that you get the structure based on the correlation chart. So here is the example of IR spectrum. Okay, IR spectrum. So here is the IR spectrum. The y-axis is a percent transmittance, and x-axis is a wave number. So under this, if you see this IR spectrum, actually it can divide it into two. One region, which is between 4,000 to 1,000, 1,500 is for the stretching vibration, a very common functional group that we can obtain here. And below 1,500 is the fingerprint for each of the organic compound or each of the sample. So for example, like salicylic acid, we need to assume that in the sample it has a really high purity of salicylic acid, because if there is a mixture of other compound, it will give many peaks or many bands in the IR spectrum. Okay, so this is for the salicylic acid that contain C double bond C or H C double bond O. Okay. Okay, this is the IR spectrum for glucose. Okay, so glucose, we know that this is structure of glucose. So it has a lot of OH. So it will show the peak for OH here. So I will not go into deep on the interpretation of the IR spectrum yet. Just want to give you the overview of the IR spectrum, what you will get after you run your sample using IR spectrum. So this is actually the spectrum that you will get. But in order for you to interpret this, you need to understand the basic principle of the IR spectroscopy. Okay. Ni IR spectra. IR spectra is the combination of many IR spectrum. It's a plural for IR spectrum. A2 here, the blue one is IR spectrum for A2. The red one is IR spectrum for A5. So you need to understand the term that you use. Okay, not spectrums, it's a spectra. And then this is what we call it as a stacking IR spectra, because in one infrared what do you call this infrared spectrum here, infrared one graph, in one graph there is a 3 spectrum, so we call it as stacking, because sometimes they come up with the results stacking, or they come up with an individual IR spectrum. Okay, it's based on what you want to determine. Okay, and then sometimes you can actually specify the range here. Okay, the typical one, not the typical lah, the whole range of IR spectrum is 4,000 to around 450. Okay, but then if you want to know the specific bands of peak, it's 1,400 to 400, for example, like this one. So these are specific peak, and we call it as IR spectra. There is also IR spectrum with absorbance value, but it's actually the what do you call this? The intensity is different or opposite of this transmittance. But I like to use transmittance actually. It's all the same, but I like to use percent transmittance. Okay. So this is how we can interpret IR spectrum. So inside this IR spectrum, okay, if you are not familiar with IR spectrum, so you will just get this peak, okay, bands. You have a wave number and also percent transmittance. Well, actually the peaks, or sometimes we call it as band, peak or band. So these are the term. If you use the word peak, just use peak. The peak represent the bonding with what kind of bonding, very specific. But if you say it is band, the band at 3032 represent the CH stretching for aromatic. So this is the wave number, this is the band, this is the bonding CH, this is the additional information, whether it is aromatic or alkyl. Okay, and stretching is the vibration mode. And then some of the what do you call this? Looking at some of the researcher looking at the intensity, but some of them is not. Okay, but however we can call it as sharp, and we can call this peak as sharp and strong peak, because there are actually other peaks here, but these peaks maybe come from the impurities. Okay, this small peak come from the impurities. Okay, so this is an example of the spectrum for toluene. Okay, this statement is actually come from the course learning outcome of my subject, Bioorganic Chemistry, the final one. Okay, the course learning outcome number 4. So it's stated here, interpret results from infrared spectroscopy using a correlation chart. So student will what do you call this? Will use correlation chart in order to interpret the result that obtained from infrared spectroscopy. Result that obtained from infrared spectroscopy is the IR spectrum or IR spectra. Okay, so what is a correlation chart? Okay, so correlation chart is infrared spectroscopy correlation table or correlation chart. It's a list of absorption peak or the band value and frequencies typically reported in wave number for each of the common types of molecular bonds or and functional group. So molecular bonds and functional group such as OH, CH, C double bond O. So those are considered as bonds and also functional group. Okay. This is an example of the correlation chart. Correlation chart ni can be in various form. Okay, it can be in various form. If you Google correlation chart for IR, there is so many what do you call this? Can give many types of correlation chart. This is the simplest one because just give only bonding, CH, OH, and H, and this type of compound, and it give a range. So CH correlation chart will give you information about the position of this bonding at the infrared spectrum. So the range for this CH is 3100 to 2800. The range for the OH is 3700 to 3300, and this OH for the alcohol. And so on lah. Okay, I will not go into depth. I just want to give you example of the correlation chart. There are another correlation chart based on this illustration. Okay, so it start with 4000 to 1000 only. If there are bands at around 3000, 3300 to 2800, so the peak or band referring to the CH bonding. Okay, if there are peaks at 2300 to 2100, so the peak may be at the peak represent C triple bond C and C triple bond N, and so on lah. So these are the fingerprint region. Fingerprint region meaning that if there is a specific peak, okay, and considering the sample must be highly pure, okay. For example, like what you see in the previous slide, okay, there are certain peak at this range, and this actually represent this compound, okay. For example, like butane. So there is a specific peak for the butane, okay. There is a specific peak for the salicylic acid at this region. This is another example of a correlation chart. Okay, so you need to understand the basic principle of infrared spectroscopy before you can interpret the eye spectrum. Okay, because the correlation chart is come up with various what do you call this various form. Okay. Okay, so this is the result from IR spectroscopy again. So these are all this peak or bands is actually based on the correlation chart. We can say that CH stretching ni, okay, we can refer to the correlation chart here, and there are actually peaks at 3000 something here. So this is for the CH. How do we know that? Because of the correlation chart here. Okay, because of this correlation chart. So on lah. Okay, so we'll go into deep about the infrared spectroscopy. Dr. Razodin, do we have break ke ataupun
Yes,
Q&A ke dulu?
actually, we can straightforward. So it's only 1 hour. So you
Okay.
have another 15 minutes, so-called about 15 minutes, and then we have the Q&A sessions. There are any questions, right?
Okay, right, that's good. So I will continue this, and then if you have any question, you can ask me after this apa nama tu talk. Okay, so infrared spectroscopy, as we know that it is an interaction between matter, and matter tu is your sample lah, and electromagnetic radiation as a function of the wavelength or frequency of the radiation. And infrared spectroscopy is the measurement of the interaction of infrared radiation, very specific. We use the infrared light with matter by absorption, emission, or reflection. So it is used to identify chemical substance or functional group in this form, whether it is in the form of solid, liquid, or in the form of gas. So there are actually what do you call this different electromagnetic radiation. Okay, we have a visible, infrared, ultraviolet, microwave, and also radio wave. Okay, so actually if the okay, so infrared light is a photon, or it is a electromagnetic waves. So this is a molecule or your sample or any matter, whether in the form of solid, gas, or liquid. So once we give the photon energy, so the molecules will absorb this photon energy, and then the molecules energy is increased by an amount equal to the photon's energy. And then after that, okay, the instrument will change this energy value to the IR spectrum. Okay. Actually, in order to understand really into deep about this mechanism, actually you can refer to lecturer from the Department of Physics or from the chemistry. Okay. So these are the effect of electromagnetic radiation on molecules. So if you can see here, the gamma rays is the highest one. Okay. So gamma rays, X-ray, and so vacuum UV, it has a higher energy, higher frequency, and shorter wavelength here. Okay. And it will ionize the molecules. And that's why actually gamma ray ni is very dangerous to human because it can ionize our what do you call this? It can ionize our skin, can affect our body. Okay, for near UV and also visible, is electronic transition. Okay, the molecular effect is electronic transition. This one infrared. So once we give the infrared light to the sample, so there will be a vibration happen to the molecules. Vibrate. Okay, bergetar. And for the microwave, there is a rotational motion. For radio, is nuclear spin transition. So, once we give the infrared light to the sample, it will vibrate. We can see, we want to see what is the vibration, what are the types of vibration, or what happened to the molecules actually. Okay, so it's related to the theory about the vibrational energies of molecules. If you can see, so the bonding in the organic compounds, these are the example of the bonding in organic compound. CH, like I told you before, we have CH, C double bond C, C double bond O, and so on lah. So for this is it's like these two atoms here is like this one. If you can see the illustration here, they're connected by a string. So once we give energy, whether we stretch it or we compress it, we need to give energy. And this energy, okay, the vibrational frequency is related to the potential or related to the energy. Okay, this is how the sample will vibrate. So this is the molecule of water. Okay, the simpler molecule, it can stretch, okay, asymmetric stretch or asymmetric stretch, or it can bend, libration, and so on lah. So there are actually for the water molecule, there are 6 common vibration modes. Okay, if you can see the sample here, so these are the vibration happen to the molecules once we give the infrared light. So this energy, okay, happen here, change to the infrared spectrum. Okay, so for the molecular vibration, the frequency of the stretching vibration depends on 2 quantity. Okay, the first is the mass of atom, the difference between one atom and another atom. Okay, for example, like C and also H. Difference between C and H will affect the frequency. Okay, and also the stiffness, rigidity, inflexibility, hardness of the bond. For example, like C single bond C, C double bond C is much higher than the C single bond C. C triple bond C, the stiffness or the strength is much higher than the C double bond C. Similar to this one. Okay, C double bond O, carbonyl group, the energy is much higher than C single bond C. That's why it's actually it can affect the frequency, and then it can affect the position of the peak or band in the IR spectrum. Okay, so CH, it has a higher wave number as compared to the CC, and because the difference between the carbon and also hydrogen. Okay, you can see actually refer to the periodic table. And C triple bond C, it will show at higher wave number as compared to C single bond C. In fact, for the C single bond C, we cannot observe it in infrared spectrum because the energy is too low as compared to C triple bond C. Okay. C triple bond N, it will show at higher wave number as compared to C single bond N. And C double bond O, 1700. Okay, some of the compounds, for example, like ketone or aldehyde, it will give a very sharp peak at 1700 because it has a C double bond O. And this is an example of infrared spectrum of 2-methyl-2-butene. Okay, it has C double bond C, but C double bond C is located at the middle. Okay, so that is actually some of the symmetry condition that will not give a stronger bond occur for the C double bond C. So C double bond C will appear here. The peak for C double bond C or band for C double bond C will appear at 1660. How do we know this? It's based on the correlation chart. Okay. CH bending vibration for this compound occur here at below 1500. So you see how I translate this IR spectrum. Okay. This peak of band referring to the bonding vibration. Okay. CH is a bonding, C and H. And at this position is for the stretching. Stretching is a vibration mode. Okay. So heavier atoms vibrate more slowly than lighter ones. Stronger bond are generally stiffer, requiring more force to stretch or compress them. So that's why CH at this position as compared to CH, this one is different vibration mode lah, as compared to C double bond C or C single bond C. Okay. So in a simple compound H2O, IR spectra or IR spectrum contain many different absorption. We call it as absorption. Not just only one absorption for each bond, but many of these absorption result from the what they call this stretching vibration of the molecule as a whole or from bending vibration. Okay. Like for example, for H2O, there is a symmetric stretching occur here more than 3000. Okay. Anti-symmetric stretching and also bending or scissoring will occur at around 1700. Okay. So for one simple compound, it's not just only one peak or one band because it has a lot of what you call this vibration modes. So imagine that if we have vanillin, for example, vanillin. So vanillin contain various bonding here. Contains a lot of functional group OH, C double bond O. So it will give result on the stretching and the fingerprint region here is for the bending or other vibration modes rather than stretching. So if you can see here, we can divide this IR spectrum into two. One is a simple stretching vibration between 4000 to 1600. So this is for the stretching of the CH, okay? And these are some peak for the stretching vibration. This one is for the C double bond O, this one is for C double bond C. And this is fingerprint region 1600 to 400. And this is specific, there are specific peak for the vanillin if the sample is really pure or highly pure. Okay. Okay, IR active vibration. In this sample, in the, what do you call this, in one sample, in one structure, it has a, it can be active or is inactive. It depends on the, what do you call this, bonding here. Okay, I think for the active vibration or inactive vibration, I think we will discuss this in part 2 because it's more complex. So this is example of IR spectrum for the N-octane. So N-octane ni because it just contains CH. Okay, there is no O, there is no NH. So there is a CH stretching, scissoring, rocking. So it's just only a few peaks only. Okay. So as a summary, the basic principle behind the IR spectroscopy is the vibration of the bonding. The CH will vibrate once is interact with the IR light, and it will give bands at around 3000. Is around 2100. So the vibration actually, the mode of action is vibration. And for the in the IR spectrum, there are two regions. One is stretching vibration, stretching, and also another one is fingerprint region. And all of the peaks or bands represent bonding or functional groups. And we actually use correlation chart to interpret those IR spectrum. So the important thing is that you need to know the functional groups or bonding in the sample for you to interpret the IR spectrum. So I think we can see you again in the interpretation part 2 interpretation of IR spectrum. Okay. For we learn this IR infrared in actually in chemistry department. During my first degree, I learned this subject. I learned the subject of spectroscopy only in one whole semester, because we need to understand the basic principle behind that spectroscopy technique. So hopefully to see you again on part 2 and also part 3. So Dr. Rizadin, I think with that, thank you very much.
Right, thank you very much, Dr. Nick, for covering the first stages of FTIR for the basics, which is covering the principle. You're also mentioning about the correlation chart, and also examples of what we call it, the spectrums and spectra. So now we are going to open for Q&A sessions. So you can raise your hand, can speak to the mic, or you can also type the chat in the chat box. So any questions from the students or from the staff PPS? Anda boleh menggunakan bahasa Melayu dan juga boleh menggunakan bahasa Inggeris. Bahasa lain tu kena buat translations lah.
Boleh je nak cakap bahasa Arab lah.
Ada? Tak ada soalan? Agaknya semua agak faham kot sebab basics principle. I hope so. Daripada PPS, daripada staff, ada soalan?
Doktor, saya ada soalan.
Okay, go on. Introduce your name.
Saya nak tanya.
Ask question.
Nama saya Putri dari 4 SSCG. Saya nak tanya. Tadi doktor ada explain kalau nak tahu structure, kita kena combine dengan ada instrumen. Tapi kalau contohlah, kalau saya cuma nak tahu functional group je, perlu ke saya guna instrumen lain juga combine?
Okay. Kalau nak tahu functional group sahaja, actually it depend on the sample tu. Sometimes tu sample tu is not pure. Dia ada combination of others sebenarnya. Okay. Kalau sampel daripada panggil apa? Putri ke Najihah?
Ya, saya Putri Najihah.
Putri Najihah. Okay. Kalau sekarang ni sampel tu sampel apa?
Apa?
Belum tahu lagi. Untuk ada buat ni kan PSM kan tahun ni. So kalau sampel tu sampel apa tu? What kind of sample? Palm oil punya ni lah. Okay. So kalau palm oil punya apa nama tu? Dia ada various, dalam tu dia ada macam-macam organic compound kan. So macam-macam organic compound tu it will give macam-macam peak lah dekat sini. Okay. Tapi kalau if for example from pomade tu you extract something, for example like tak tahulah mungkin ada something yang certain compound yang very specific, kalau tak pure pun mungkin dalam 60% punya purity, so it will show apa nama tu important peaks. For example like kalau macam kat sini dia akan show, kalau kat sini 1700 ni mungkin ada peak untuk C double bond O. So apa yang kita boleh kata, the sample contain C double bond O lah. Okay. Ataupun kita boleh expect, we can expect some of the compound under bawah pomade tu that you extract. Okay. Saya pun tak tahu sangat berkenaan dengan pomade ni. Okay, for example like this one, cellulose. Okay, cellulose lah that you extract from plant, cellulose. Okay. Cellulose ni dia contain apa dia? Kalau macam ni kalau tengok daripada structure ni, structure ni cellulose structure kan. So that's why it's important sebenarnya for the student, if you extract something and then you want to use infrared spectroscopy to characterize your product, so under chapter 2 literature review tu, it's better for you to put the structure of the sample. If you want to extract cellulose, put the structure of the cellulose. Why? Because the structure of the cellulose ni will give information in the future, especially on the IR spectrum. So you extract cellulose, you expect to get OH. Jadi banyak OH lah. You extract apa nama tu cellulose ni, you will not get C double bond O kat sini. Sebab there is no C double bond O unless it is oxidized ke or it has impurities. So if you have C double bond O from your sample, if you have a peak for C double bond O, meaning that there is some impurities in your sample, or maybe the sample to oxidize to something. Okay, faham tak Putri? Jadi itu untuk functional group. And then no need to have other instrument lah. Okay, no need to have other instrument lah. Just to know the functional group, itu pun dah cukup dah. Okay.
Oh, faham.
Right.
Tapi in the future, let's say for example level tu tinggi sikit, you are doing master ke, you are doing PhD ke, or maybe you want to confirm that your sample tu, it's better to have combination lah. So bila kita combine tu, kita ada support the result not just only from one, but we have a support from others lah. Okay.
Right. Okay.
Terima kasih Dr.
Right. Thank you Dr. Nick. Macam soalan Putri tadi asking about pretty much like a raw extracts, that is going to be very difficult because I think Dr. Nick bagi tahu tadi there will be a lots of peaks coming out and there is plenty of things. Such as in pomade kan, you will have flavones, you will have flavonoids, you will have terpenes, you have lipids, you have everything in there. So perhaps normally you can do extractions like Dr. Nick said. You can do successive extractions, for example from polar to non-polar, and then once the polar, you've got the polar extractions. For example, stop with non-polar, hexane, and then going into polar. So you've got that polar, you put it inside there, so definitely you will find only what we call it, some compounds that are polar. The non-polar already being screened earlier, getting rid of. Right, thank you Putri for asking that question. It's very, very good questions actually. Thank you also Dr. Nick about giving us more understanding regarding the usage of FTIR, right? Because some of us might thought that, oh, just extract a sample, for example, dia extract je terus masuk kat dalam tu and hoping to get something. It's going to be a headache to crack all the compounds inside. Right, do you have any more questions?
Sini we have a FIUP student kan? Kan? Banyaknya FIUP student.
Students, yes.
PSM student or maybe master student lah. Okay.
Uh,
Actually, IR spectrum ni is one of the technique that you can use to confirm not just on the functional group. You can actually see the effect of, like what Terazaudin said, that effect of extraction. You have the raw, you have a raw sample, and this in this raw sample you have a lot of what they call this compound inside there, and then you do the extraction. You hope that you can remove some of the compounds you want to have a specific. So what you can do, you can make it, you can apa nama tu, analyze the you can, what do you call this, analyze the sample using a spectrum. Okay, and then after extraction you analyze it again, and maybe after another extraction you analyze it again. So you, for example, you get 3 IR spectrum here. So the first one, blue one, is the raw material, for example. Second one is the red one is the second extraction. So some of the peaks are changes, or some of the peak are apa nama tu, removed. And then the final one is A7. Like for example, A7 here, the black IR spectrum here is for the final extraction. So there are actually some changes once you extract, once you do this extraction. Okay, because we hope that some of the compound will be removed during the extraction. So it's not just only the final product that you analyze using IR spectrum. You analyze it starting from the raw until you get the product. And also, like talking about cellulose, right? Cellulose also, you can actually run the IR spectrum for the raw cellulose, and then you want to purify it, you want to increase the punya content. So again, you do this IR spectrum, and then you do you come up with 5 times treatment. So each time you save it, some sample and do the IR, you get the spectrum, and then you stack it, stacking, and you can see the difference. Okay, so you're not just only you're not just only referring to the previous paper talking about this treatment can remove some of these carbonyl compound, but you have the data from the IR spectrum. Okay, kena bijak sikit lah to design your apa nama tu experiment lah. Okay.
right. We can allow one more question, last questions. Maybe perhaps from the staff. Kalau tengah nak buat ada yang staff on thinking of doing research, looking at this, can really ask Dr. Nick, because okay.
Semua faham lah tu kot.
Semua faham lah tu kot.
So hopefully nanti bila saya baca thesis tu nanti tak ada mistake lah. Kadang tu nanti bila baca thesis student ni, okay, nanti macam-macam lah benda yang berlaku yang tak sepatutnya ada. Okay. So for the student, if you need my help to design the apa nama tu, to design your methodology ke, or to interpret the spectrum ke, not to interpret lah, to help you to interpret that spectrum, do not hesitate to contact me lah. Okay, tak ada masalah.
Right, jika tak ada apa-apa, so kita end our sessions, and hopefully we're going to see each other again on December on GC Physics Principle. Okay, thank you very much for everyone. Make sure that you already masukkan kehadiran dalam link yang diberikan ya. Nanti rugi pula, dah datang tak dapat pula point. Okay. Right, thank you. Assalamualaikum warahmatullahi wabarakatuh. And have a nice weekend, everyone. And thank you also to Dr. Nick for having this session.
Okay, thank you very much.